Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, in this video, I would like to continue the new chapter. This is the chapter called displacement. Actually, in the bigger space, this is actually part of displacement method. We call this as moment distribution method. So this is actually I take this from the textbook. This is actually the textbook, the ebook, that I have shared. I have shared to you in the beginning of the semester, Hibbeler textbook. So under the Hibbeler textbook, moment distribution method, we have we have in chapter 12. Chapter 12 for moment distribution method. And chapter 11 is actually slope deflection method. So in this moment distribution method, some of the theory regarding free body diagram of beam, what is actually fixed end moment, how we apply fixed end moment, what is actually the output, because moment distribution method and the previous method called slope deflection method has the same same output. The same output. It is actually member stiffness, member and moment. Member and moment. So the output is member and moment. So we are going to use this moment distribution method in order to determine, or in order to analyze member and moment in the structure. The structure, there are two types that we gonna analyze. It is beam as well as frame. Okay. Moment distribution method is one of the famous method. This is very famous method to analyze the internal moment. Actually, member and moment in beams and in frame is actually internal moment, and the internal moment we use to draw the bending moment diagram in the beam as well as in the frame. So I will briefly introduce in this video. I will briefly introduce about moment distribution method. The key concept. So of course this is for indeterminate structure. This is for indeterminate structure in indeterminate beam and frame. Beam and frame. So I want to move to the important terms that everyone should understand. Okay, number one, this is number one important things that we must know. Okay, it is sign convention. Sign convention. So sign convention we use in moment distribution method is clockwise positive. Clockwise we assume as positive. Clockwise moment that act on the member are considered positive. Act on member considered positive. Okay, so this is about the sign convention. Okay, next thing is fixed end moment. Fixed end moment. Fixed end moment, we have actually used this previously under chapter number 2. Chapter stiffness method. Stiffness method. At that in that chapter, we use fixed end moment or fixed end reaction to analyze or to calculate what we call as equivalent element nodal forces. Okay, so we actually distribute moment. Okay, distribute whatever forces that is subjected on the member to the nodes. And because it is fixed, okay, both and fixed, and we must understand that internal forces we also assume as fixed. Okay, because internal forces, because internal joint, okay, has the moment value, has the moment value. So that is why all internal joint has moment. It is called as member and moment. So we have to use to use both and fixed, to assume as both and fixed. So we use fixed and moment, okay, in the previous chapter, and also in this chapter. Okay, and fixed and moment is important because we use this as first moment value in the table, because we will distribute moment distribution method. In this moment distribution method, we will actually distribute moment in the table, distribute moment in the table using joint moment times with distribution factor. So the first moment that we are going to distribute, okay, is actually fixed end moment. Fixed end moment. So we will use the same appendix. Okay, normally the beam where it is subjected to UDL or triangular load or point load at the center or point load not at the center but still on the member. Okay, is actually it is actually fixed end moment. And fixed end moment is actually the first member and moment in the table, because we get joint moment from fixed end moment. Okay, so it is about fixed end moment. Okay, fixed end moment. And one thing that everyone should understand is for fixed end moment, the sign that we put, whenever we calculate fixed end moment is actually the behavior. Okay, not assumption. So we put negative or positive depending on the sign convention that we have chosen. We put sign convention for fixed end moment based on clockwise positive sign convention. Okay, so fixed end moment. So fixed end moment. Okay, and then we have to understand about what we call as member stiffness factor. Member stiffness factor. So we need to remember, okay, to remember two formula to calculate the member stiffness factor. Member stiffness factor. The word stiffness we actually used previously in stiffness method, but in moment distribution method we use stiffness factor not in matrix form, okay, but in single value. So the symbol is K. The symbol is K, and it is equal to 4 EI over L. So K is stiffness. It relates with rigidity of the structure. So E is modulus of elasticity. I is moment of inertia, L is length of the member, and there are two conditions that we need to know, that we need to understand. Okay, the first one is called as far and fixed. So why it is called as far and fixed, not both and fixed? Because we use the term far and fixed. We use the term far and fixed because if we have one structure like this, okay, if we have one structure like this, we have A B C and D, and we have to calculate member stiffness factor for member AB, for member BC, and for member CD. Okay, for member CD. So for each member, we have to apply for an fixed K formula. Okay, for n fixed K formula. So for n fixed referring to this, for n fixed. Okay, one is internal. This is internal. Or in this case, if we start from, if this is A, this is B. Okay, B is actually internal. This is internal. Okay, internal is always assumed as fixed. So NA is called as far end. So this is the far end. Far end. So it is far end fixed. So for far end fixed, we use 4 EI over L. 4 EI over L. Okay, 4 EI over L. And for BC, because both B and C are internal, so straight away we will use, okay, we will use this as 4 EI over L. So AB also we use 4 EI over L. And for CD, what about CD? So for CD we have like this, C and D. So this is D, this is C. This one is internal. So far end, so this is far end. Means end of the structure, far end. Okay, far end is fixed. So this is far end fixed. So we use, again, this is also 4 EI over L. Okay, means that we have to identify the member stiffness for each element in the structure. So this beam has three members. So we have to calculate or to identify the member stiffness. So internal is fixed. So for BC, we use 4 EI over L. A and B, A is far end fixed. So we use 4 EI over L. For CD, D is far end. Okay, C is internal. So far end fixed referring to D. So we also use 4 EI over L. Okay. So this is very, very important because from member stiffness, we will calculate joint stiffness, and after that, we will determine distribution factor. Okay. So I will jump straight away to all that is important for you to understand. Okay, joint stiffness factor. Joint stiffness factor is actually means that we have member, we have joint. We have member, we have joint. So in order to to calculate moment or to distribute moment, we have to have what we call as distribution factor. And to calculate distribution factor, we must know joint, what the value of joint stiffness. Okay, joint stiffness. Previously, we calculate member stiffness using formula. Okay, and when we combine, we will get joint stiffness. Okay, joint stiffness factor. joint stiffness factor. So joint stiffness means if you want to, we have joint A. Okay, joint A. So based on this one, joint stiffness is 1,000 plus 4,000 plus 5,000. Okay, and okay, what most important is we must know that, we will calculate distribution factor, and formula to calculate distribution factor is this one. Okay, this is distribution factor. The label is DF, and this is equal to K divided by total K. K divided by total K. Okay, for example, if K is given, okay, let's say we refer to this figure 12.4 B, A, B and C. So in this case, the member stiffness, okay, K we have, okay, from this frame we have member AD, member AB and member AC. So member AD, the member stiffness is 1,000. Member AB, okay, 1,000. Member AB, the member stiffness is 4,000. And member, okay, member AC, the member stiffness factor is 5,000. So to calculate, because one element only have one one uh, one value of K. Okay, one value of K. So if we want to calculate K for member AD, okay, K for member no K K for, we know the K for member AD. If you want to calculate distribution factor, we must understand that distribution factor we identify, okay, at each end, okay, at each end, not only at joint A. So if we draw this free body diagram, draw the free body diagram for this frame, for example, so we will actually resolve this into three element, like this. Okay, three element like this. So distribution factor means if we have only one value of K for one element or one member, so for member AD we have one value, for member AB one value, for member AC one value, just like what we have done previously in stiffness matrix method, where we determine the element stiffness matrices. But whenever we want to calculate distribution factor, we have to understand that distribution factor, number of distribution factor is actually equal to number of member and moment in the structure. Member and moment in the structure. So by looking at this, there are three element or three members, three element. We have member AD or DA, we have member AB, we have member AC. So we must understand that one element consists of two nodes. One element consists of two end. Okay, so how many member and moment? Okay, how many end? One member one member has how many end? It has two end. So one element has two member and moment. So member and moment we label as this. Member and moment. So for one element we will have two. Okay, for one element we will have two end. So and at each end there are moment. So we will have one element with two member and moments. And number of degree of freedom, number of distribution factor, DF. Number of distribution factor we must calculate equal to number of member and moment. So from this, okay, we know that there are three members, so there are six member and moment. So this member and moment is actually the output. the first output that we are going to calculate or to analyze. So means that we will have 6 distribution factor. Okay, so we will label the member and moment for this frame as M. So label the joint first. So this is D. This is D, not A. Okay, this is D. This is A. This is A. This is B, A, and C. So we have MDA. We also have MAD. Okay, we have MAB, MBA. Okay, and we also have MAC and MCA. And all these 6, okay, are actually called as member and moment. There are 6 member and moment. 6 member and moment. And member and moment is equivalent to 6 distribution factor. Distribution factor or DF. So in this diagram, there are 3 members. There are 6 member and moment. So there are 6 distribution factor. So how to calculate distribution factor? Okay, how to calculate distribution factor? By using the formula, because the distribution factor is actually equal to K for element divide by total K for that particular joint. Okay, so if we are going to calculate distribution factor for, okay, if we want to calculate distribution factor for A, not A, it is DA, and D is fixed, and it is actually equal to K DA divided by K DA plus infinity. Okay, plus infinity. So why it is infinity? Because fixed end means that it is not the end of the structure. We must plus by infinity. End of structure is cantilever end. End of structure is roller end. Roller support. End of structure is pin support. But fixed is not the end of the structure. So we have to plus with infinity, and we will get this as 0. As 0. Okay, so we actually have this. Okay, KAD. And we can, it is actually the same with KDA. It is actually the same thing. Okay, and this is equal to 1000. 1000. And we have KAB, which is the same with KBA, and the value is, I think, 4000. And we have KAC, which is also equal to KCA. It is actually the same thing, just the matter of writing, so that it will help us to understand later on, okay, why we have to write it like this. Okay, 5000. This is K. So to calculate the FDA, distribution factor for DA, because D is actually fixed end, and fixed end we must to plus with infinity. So the distribution factor is equivalent to 0. Okay, next, DFAD is equal to Okay, KAD, member stiffness, divide by K joint. It is joint stiffness. A connect with AD. A connect with AB. A connect with AC. So this is equal to KAD is 1000 divided by 1000 plus 4000 plus 5000. And this is equal to 0.1. Okay, 0.1. Okay, because joint stiffness means Ka. Okay, joint stiffness means Ka. This is Ka. This is Ka. AD is member, A is joint. Okay, so we move to the next distribution factor. We have DFAC. For DFAC, to calculate K, it is K. We just referring to back to this, it is AC. So we put AC. For member, is member AC. And it will divide by KA. Okay, and KA is actually, this is 4,000 divided by 10,000. So this is equal to 0.4. 0.4. And then we have DFCA. And DFCA is equal to, so we refer back to this. Okay, it is K. It is actually KAC, but we write in CA. Okay, so that we do not confuse. Okay, it is KC. So KC is KCA plus infinity. So this one we get 0. 0 because of this is fixed n. Okay, fixed n. Then we move to DFA. Wait. AC, AD, AB. So AB, this is AC, right? AC is 5,000. 5,000. So this is 0.5. Okay. So move to DFAB. DFAB. So DFAB is actually KAB divided by KA. And KAB is 4,000 divided by 10,000. This is equal to 0.4. And then for DFBA, we have KBA divided by KB. And KB is equal to KBA plus infinity. And this is equal to 0. So in total, there are 6. Okay, there are 6 degree distribution factor. 6 distribution factor. Okay, 6 distribution factor because 1, 2, 3, 4, 5, 6. No, not from this. It is 6. Okay, 6. It is 6 DOF. Sorry, 6 DF. 6 distribution factor because we have 6 member and moment. Okay, 6 because we have it is 6 distribution factor because we have 6. Okay, 6 member and moment. Okay, member and moment. Okay, so since there are 3 zero value which is referring to far n fixed at B and fixed at C and fixed at D, yang ni. Okay, and D, and B, and C. So all these distribution factor are 0. So we have the value for DFAB, DFAC, DFAD, which is equal to 0 0.1, 0 0.4, and 0 0.5. So whenever join A, because in moment distribution method, we will distribute moment using join moment. Join moment we times with distribution factor. Okay, we times with distribution factor, and at A the join moment is 2000. At A the join moment is 2000. So M at A is negative 2000. M at A is negative 2000. So by looking at distribution factor label, okay, we will have six. We have six member and moment. We have six member and moment. Okay, we have M, D, A, which is equal to uh, MD times with distribution factor DA, and this is equal to 0. And we have MCA is actually equal to MC, because it is, okay, we're referring to join. Okay, referring to join. MC we times with distribution factor CA, it is 0 factor, so it is equal to 0. And we have MDA. MDA is actually MD, moment at D, times with distribution factor DA. DA, so this is equal to 0 because distribution factor is 0. So we have remaining 3. It is MAC. So MAC, what we need to do is we have to have MA times with distribution factor AC. And this is equivalent to, okay, wait. It is negative 2000. It is negative 2000 times with 0. Okay, we start with DA, not DA. Another one is B. So this should be B. B and B. Okay, so this one we start with D. Okay, AD, FAD. Okay, FAD is 0.1. The FAD is 0.1. So we get negative, okay, we get negative 200 kilonewton meter. Okay. And MAAC is actually M at joint A times distribution factor AC. So this is equal to negative 2000 times with AC is 0.5. So it is equal to 1000 kilonewton. And we have MAB, which is equal to MA times distribution factor AB. So we have negative 2000 times 0.4 the factor, and this is equal to negative 800 kilonewton. Okay, so this is actually the process that we are going to apply in the table. In the table, we do it in the table, and we do it uh, okay, repeatedly. Okay, we repeat the process again and again, until the final moment, until the process, the moment reaches zero value. Okay, and one thing is the total moment must equal to zero. So okay, the total moment is zero. So whenever we distribute, we must get the total moment. Okay, the total moment which is equivalent to zero. Means that we will get the total MA which is equivalent to zero. Okay. Okay, doesn't matter about sign that is shown right now. So I will show to you the actual example in the table. Okay, what we will do is, okay, of course, the next term after distribution factor, we need to know the carryover factor, and for fixed end moment, the carryover factor is equivalent to 0.5. So we are going to use this to carry over the moment to the adjacent. Okay, to the adjacent. So I want to choose one example. Okay, one example, not this one, not this. Okay, wait, this is the procedure. Okay, I want to refer to this, okay, as the example. Okay. Okay, now. Okay, this is example 12.1 in the textbook. Okay, in the textbook. So we have A, B, C, D. A and D are fixed. B and C are roller. But remember that internal B and C is always assumed as fixed. So for K value, for K formula, we are going to apply for each element 4EI over L for each element. So remember that one member, we have one stiffness factor. One element, we have one stiffness factor. So it is K for member AB, K for member BC, and K for member CD. Member AB has 12 meter length, BC also 12 meter length, and CD we have 8 meter length. 8 meter length. So we get like this. KAB is 4EI over 12. KBC 4EI over 12. This. And KCD is 4EI over 8. 4EI over 8. So from this K value, we can calculate distribution factor. And how many distribution factor that we have in this beam. Okay, so we have how many element? We have element 1, we have element 2, we have element 3. And one element consists of 2n. One element consists of 2n. So 2n, so we have 6. It is 2, 2, 2. So there are 6 distribution factor. 6 distribution factor means that we will have 6 member and moment. member and moment. So to calculate distribution factor, remember that A and D, since both A and D are fixed end, so distribution factor for A, B, and for D, C, we know that it is equal to 0. Equal to 0. Actually, we can, okay, this is the formula. It is DF. Okay, DF, it is K divided by, okay, K divided by total K, or K join. Or if we want to calculate, for example, DF for AB, we have to have KAB divided by KA. And if we want to calculate DFBA, we have to have KBA divided by KB divided by KB, and KB consists of BA and BC, so this is KB. So if you want to calculate DF for BC, it is actually KBC divided by KB. So if we want to calculate, for example, KCB, okay, it will equal to DF, DF first. Okay, if you want to calculate DFBCCB, okay, DFCB, it is KCB divided by KC. And if you want to calculate DFCD, it is equal to KCD divided by KC. And if you want to calculate DF for DC, it is actually KDC divided by KD. And since at A and at D, okay, both A and D are fixed, so we will get this as 0. We will get this as 0. So we have 4 distribution factor to be determined. Okay, 4 distribution factor to be determined. So I want to determine this, okay, by, okay, let's say we have, I want to do it like this. Okay, like this. Okay, we have join. We have join. We have member. Okay, member. We have K. Okay, K value that we get. Okay, in this example is in terms of EI. So K in EI. Okay, and then distribution factor. Distribution factor. So we have, okay, we have join A. Okay, we have join A. Join A, member A, B. And then we have join B. Join B, we have BA and BC. We have BA and BC. And then we have join C. Okay, we have join C. We have join C, CB, and CD. And lastly is join D, it is DC. Okay, Okay. So KAB and KBA, KAB and KBA is actually one value. Okay, K is not for element, for not for N. K is for member. So we get because leg is 12. Leg is 12. It is actually 4 EI divided by 12. But since we have put EI, okay, beside K, so we only put value in the table. So it is 4 divided by 12. 4 divided by 12. Okay, these two is the same value. And then for BC and CB, the same value, the same thing. Again, it is 4 over 12, 4 over 12. And then for CD, it is 4 divided by 8. Length is 8. So this is also same. Okay, and distribution factor for A equal to 0 because it is fixed support. For D equal to 0 because it is fixed support. And then, okay, to calculate distribution factor, it is, remember that it is for BA, for DFBA, so it is BA divided by B. Okay, BABC, okay. So it will equal to 0.5 and 0.5. So this is 0.5, this is 0.5. Okay, and for CB, it is actually 4 over 12 plus total 4 over 12 plus 4 over 8. It is 4 over 12 divided by 4 over 12 plus 4 over 8. Okay, and the value is, it is CB, it is 0.4. 0.4, and when we know that CB is 0.4, so CD, of course, we will get 0.6. Why we have this? Because distribution factor will be equal to 1. Distribution factor will be equal to 1 except fixed N. Except fixed N. Fixed N only, the value is equal to 0. Okay, so this is actually how to calculate distribution factor. So this distribution factor will be using in the table. Okay, in the table, but before we can analyze the moment distribution in the table, of course, the next procedure is to calculate fixed end moment. Okay, fixed end moment. Fixed end moment. So we have a member BC. Member BC. So we will use this for, okay, for the formula. Okay, like this. Okay, this is 12, this is 20. So we determine using formula 12 WS square over 12. WS square over 12, so we get 240, 240. So we get here is 240. This is also 240. And we have member CD at the center. Member CD at the center. At the center, it is 258. Okay, and then we have moment, fixed end moment, and it is PL over 8. PL over 8, so we get 250 and 250. Okay, this value, these 4 values of fixed end moment, we have to transform into the table. Okay, into the table. So this is actually the table. So in the table, we have actually transfer all the distribution factor. that we get here to this. Okay, distribution factor 0.5, 0.5, 0.4, 0.6. Okay, A and D 0, 0. So FEM that we have just calculated like this, 240, 240. This is B and C. And then we have point load. This is 250, 250. This is C and D. So we have to put into the table. Okay, so BC, so we have BC as negative. So it is negative because it is opposite with sign convention. Okay, negative because it is opposite with sign convention. So the value is negative, positive. Negative, positive, negative 240, and positive 240. Okay, same goes to CD and DC. It is negative 250 and 250. Negative 250 and 250. Okay, so actually this is the this is actually the first member and moment. The first member and moment. Okay, member and moment. The first member and moment in the table. In the table. So we need to distribute moment, distribute join moment, distribute join moment, and remember that the total must equal to 0. Okay, the total must equal to 0. So it is joint total moment at joint B is actually equal to 0 plus negative 240. Okay, this negative 240, because we transform this as joint moment, and joint moment is opposite with member and moment, so we get the value after we distribute or after we times with distribution factor, we get positive and positive. Okay, it is actually like this. Okay, beside member we have joint. Beside member we have joint. So member A, B, member BC, and member CD. Okay, AB, BC, and CD. Okay, remember that the first member and moment, is actually come from fixed end moment. And the concept is, okay, this is the first thing that we assume. This is member and moment. And beside member, we have join. Okay, we have join here, join, and then we have join, fix. We have join, fix. And the concept is join moment is always opposite with member and moment. Join moment is opposite with member and moment. It is like this. So the moment that we distribute is not member and moment but join moment. So we will distribute this, we will distribute this, we will distribute this, we will distribute this. Okay, so what is the first member and moment value? The first member and moment value is negative 240, not this one. This is negative 240 and 240. And we have 250, negative 250 and 250. And all this is the purple one, the purple. So the purple. Okay, what we want to distribute, not the purple arrow, but the orange arrow. The orange arrow opposite with purple arrow. Okay, purple. Okay, member and moment. Okay, orange join moment. Orange join moment. So we distribute join moment. We distribute join moment. Remember, we distribute join moment. We distribute join moment. Okay, so join moment from this value, the join moment, okay, okay, this is B, this is C, okay, D, A. Okay, there's no value for moment at A. Moment at B is moment at B. Is this negative 240? This negative 240 or positive 240? Okay, which one? It is actually positive 240 because negative 240, this negative 240 is actually member and moment. Okay, we do not yet change to join moment because join moment is the orange. Okay, join moment is the orange and it is opposite with member and moment. Join moment, remember, join moment is opposite with member and moment. Okay, opposite with member and moment. So moment at B is 240. Okay, referring to the orange. Moment at C is actually negative 240 plus 250 because we consider the negative one, so it is equal to 10. And moment at D is actually negative 250. Okay, so this black one, okay, we don't put in the table. Okay, we must understand. So the moment that we distribute is join moment. So the value that we distribute is actually 240. That is why after distribution we put this. Because we distribute 240, not negative 240. And why we get 4 and 6? Because we distribute 10, not negative 10. Okay, we distribute 10, not negative 10. And then, okay, DC we get 0 because the factor is 0. Okay, so next after that, we have to times with the factor. It is carry over factor. Carry over factor. Carry over factor. And for the okay, carry over factor, we have to carry the value to the adjacent. It must cross boundary. Where is the boundary? This is the boundary. Okay, this is the boundary. Boundary between A and B. Okay, where is the boundary? This is the boundary. Boundary between B and C. Okay, we have boundary between C and D. Okay, we have this another boundary. Okay, so we have boundary. So to carry over the moment, okay, we have to carry the value to the adjacent. Okay, it must cross boundary. Okay, so what we need to use is we have to use the factor. It is 0.5 times with moment. So that's why we get 60. because we carry the value from B to A and from B to C. So that's why we get 60. Remain the same because the factor is 0.5. Okay. And then C, we have to carry to B and to D. So 4 carry to B is 2 and 6 carry to D is 3. Okay, so we get 60, 2, 60 and 3. So for this, at this level, okay, so the first value is actually fixed end moment. The first value is fixed end moment, and fixed end moment is the first member end moment in the table. And then we have to distribute moment. We find the total, the moment at join, and we distribute the moment. Okay, and then we have to times with the factor, the carryover factor, it is 0.5. So we get like this. And then we need to repeat again distribution process. Okay, distribution process. Okay, again like this again, but using the latest value that we get after we carry over the moment. Okay, we carry over the moment. We repeat the process. Okay, we repeat the process. And okay, to calculate the value of -1, -1, -24. Okay, to calculate the value of this, and this. Okay, to calculate this value, what we need to do is we have to times with the factor. Means that we have to find the total moment and times the factor. So the total moment at B is equal to -2, and the total moment at C is equal to -60. So that is why after we times with the factor, it is 2 times 0.5, we get -1, and then it is -60 times with 0.4, we get -24, and -60 we times with 0.6, we get -36. Remember that the total value must be 0. This total must be 0. This total also must be 0. Okay, like this. And then we repeat carry over. We get, okay, we get this, we get this, we get this, we get this. And then we repeat again distribution. So at distribution we have to carry the value. We don't carry value. We distribute moment using join moment times with the factor, time with distribution factor. At level distribution, join moment times distribution factor, and then we carry over the moment. We repeat this process again and again and again until the last distribution and the value reaches 0. Okay, until we get small value, until we find 0.0 something. Okay, 0.0 something. And please stop at distribution, not at carryover. Stop at distribution. Stop at distribution. Stop at distribution. Okay, so after that we will total all the moment. Okay, we will total all the moments, start from fixed end moment. Okay, because the fixed end moment is the first member end moment in the table. So we have to calculate all this value. We have to plus all this value. Okay, until the end. Okay, and lastly, after we sum all the value, we get MAB. So this is MAB. So we will get MAB equal to 62.5, and then we get MBA is negative 1 to 5.2, sorry, positive. It is positive. And then we get MBC equal to negative 1 to 5.2 until the end. And we will find that these two value and these two value, when we total, we get 0 because it will go back to the concept of roller support where there is no moment. There is no moment. That's why we get MB equal to 0 and MC is equal to 0. So this concept is actually we can understand whenever we read the explanation in the previous chapter. Not stiffness method, but the previous chapter in the textbook, slope deflection method. Okay, slope deflection method, because it will get back the concept, that the roller end and the roller, okay, the roller, when we combine as one structure beam, so if it is roller, so there's no moment, MB is equal to 0. But when we separate it as BA and BC, it will have moment. But when we combine that, we will get 0 moment. 0 moment. So this 6 value is actually the value in the, this is actually the internal moment. This is also the member end moment. And this is actually the value in the bending moment diagram. In the bending moment diagram. So from this, we can actually draw the diagram. Okay, by only referring to the sign. Okay, for example, for member AB, okay, the moment that we get is positive and positive. And actually, due to this, the diagram will be like this. Okay, we get from the sign that we get from the end moment value. Okay, and then for member BC, it is negative and positive. It is negative and positive. Negative and positive for BC. Okay, it is negative and positive. Okay, negative and positive. This is B and C. And along member BC, it has UDL. So we should get the diagram where it look like this. Okay, 1, 1, 2, it is 1, 2, 1, 2, 5, 1, 2, 5, and 2, 8, 1. Okay, and the value will be like, not the value, the diagram will be like this. Okay, and this point, the maximum moment, okay, will only be determined, can be determined using shear force diagram. Okay, this maximum moment. And for member CD, so it is C and D, and then the moment that we get from the table is negative, positive. Negative, positive. This one is negative, this one is positive, and there is a point load at the center. So the diagram, the moment, the bending moment diagram will be like this. Okay, this is straight line because it is point load. Okay, this is also the maximum moment for member CD, and we will get this from shear force diagram. Okay, so basically this is all about moment distribution method, analysis of beam. This is very simple, very straightforward. Okay, analysis of beam using moment distribution method. Okay, both A and D are fixed, so this is the process. Okay, and the diagram. Okay, finally we can plot the diagram. We can plot the bending moment diagram. That is actually the value that we get in the table. This is the value that we get from the table, not this, but this. Okay, the value that we get from the table, see, this, and the maximum moment we can only get from shear force diagram. So the green, okay, we get this from shear force diagram. So this is actually the bending moment diagram, and from this bending moment diagram we can spot or identify the crack that will be occurred in the beam. Okay, so I think that's all for this introduction session for moment distribution method. Actually, for the whole for the whole topic, this is how we analyze beam using moment distribution method. Except, of course, there are many more that we need to consider. For example, what happen if the far end is not fixed, it is pin or it is roller. So how we apply apply the process whenever the end is not only fixed but it has roller end or pin end. And what if we have to consider the settlement in the beam? And what if we want to calculate the fixed end moment in frame? Okay, in frame there are non-side sway frame, there are side sway frame. So how we are going to analyze all this? Okay, by the way, so by understanding this example, okay, this video, I think that you can be able to proceed with another example or another question. Okay, so I think that all for this session. So we will meet again in the next video. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.